In the last video we discussed the first derivative test, and actually there's another way to classify local extrema, and that's for the use of the second derivative test. Okay, so obviously it uses second derivative. So if we have again critical points occurring at x is equal to c, then if we have the second derivative at the critical point being positive, then it's actually a minimum. Now that's kind of counterintuitive, but if the second derivative is positive, then it's a minimum, and if the second derivative is negative, then it's a maximum. Now one way that I remember the second derivative test is through two friends of mine, Maxie and Minnie, and so if you look at it, it's kind of like a face, mouth, nose, and eyes. Eyes, nose, and mouth. But what this really tells you is that if the second derivative is negative and the first derivative is equal to 0, then there is a local maximum at x is equal to c. This is Maxie. And for Minnie, the second derivative is positive, and then the first derivative at c is 0, then there is a minimum at x is equal to c. Okay. If it helps you, great. If it doesn't, that's okay too. And so we're going to try to use the second derivative test with this function here to classify the extrema. So we first have to find our critical points. So look at the derivative, and in doing this you get 6x cubed minus 12x squared plus 6x after you do all the algebra. Set this equal to 0 and solve. Okay, so factor. I can factor out a 6x, and I'm left with x squared minus 2x plus 1 is equal to 0. And so then this factors further as 6x, and this ends up being x minus 1 quantity squared is equal to 0. So that means I get x. If I solve for x, I get x is equal to 0 and 1. Okay, so these are where my critical points occur, and so then I'm going to go ahead and find the second derivative. Okay, and when you do this, you get 18x squared minus 24x and plus 6. Okay, now the second derivative test says, well, just take your critical numbers and plug them in and see whether they're positive or negative. When I put in 0, I get out 6, which is a positive number, greater than 0. So this implies that there is a local min at x is equal to 6. Or at x is equal to, at 0. Okay. And so also for the second derivative at 1, I get out 0. And so the second derivative test actually fails here. Okay, so what I need to do actually is to go back to the first derivative test. Okay, so back to the first derivative test. Okay, so what I'm going to do is make a number line, and I've already classified 0, so I'm not even going to bother looking at that, but I'm just going to look at 1. Okay, and I want to determine, so I'm going to make a sign chart for f prime. Okay, and so I need to take test points, plug them in, so I'm going to maybe look at, say, f of 0.5, and I'm going to look at f of 2. Okay, plug them into my first derivative, see what happens. When I do this, I end up getting positive values for both of them. So my sign chart looks like this. Positive on both sides, meaning that if I make an increasing decreasing chart for f of x, my chart at 1, it's going to be increasing on both sides. So this is actually a saddle point. Okay, so end result, there is only a local min. Okay, and now technically we would have to go on and classify whether this is an absolute min or a maximum. And to do that, we would have to make a graph. I would recommend just plotting using Wolfram Alpha, plotting this function, or obtaining a graph of this function, perhaps on a small domain. So maybe look around 0, see what happens, and then classify it as a possible extreme value. And I think actually if you do graph this, I believe this would also be an absolute. Yeah, I believe this will also be an absolute min as well. Okay, because of the degree 4 polynomial. But that I'll leave for you to classify. Okay. Now the only thing we have yet to talk about is optimization. Okay, optimization. Essentially, the idea of optimization is you're looking for a maximum and minimum value, just as we have been doing before. Find the extrema, classify them. So typically optimizations are somewhat applied in nature. So we have this example here where we have organic waste being deposited into a lake at time is equal 0, and it decreases the oxygen content of the water. Okay, oxygen content C is given by this. We want to determine the minimum and maximum oxygen content during this time. So first thing, we want to find the critical points. Okay, and really this is going through the process of the first derivative test, especially because we're on a closed interval. Okay, so we have to keep those in mind, but let's go ahead and find the first derivative. So C prime, this is just equal to 3t squared minus 600t. And remember, we have to set this equal to 0. I'm going to factor out of 3t, and I'm left with t minus 200. So I get t is equal to 0 and 200. Okay, great. But look at the domain. Our domain only goes up to 25, so this other critical point we can't use. And also at 0, well, that's one of our endpoints. So we could go ahead and do the second derivative, but I think it would be best if we just went ahead and determined this by the first derivative test, especially because we have to do the first derivative test anyway for the endpoints. Well, we have to go through the first derivative process. So let's go ahead and make a sign chart. So all I'm really doing is putting 0 and 25 on an interval, and this will be a sign chart for C prime. So I just have to take a test point. Let's just say I take C of 1, plug that in, and I'm going to get a positive number. So that means in between here, and let's try that again. It's not a positive number, it's a negative number. I was looking at the original function. So C prime at 1 is a negative number, meaning that it's actually just decreasing all the way through here. Okay. So again, we have to think about, maybe make a little sketch here to decide whether these are maximum or minimum values, and absolute or global, mins or maxes. That's to come though. Alright, so here, if we're decreasing after 1 or after 0, so it starts up here and just decreases. Okay, so and then similarly down here, it's decreasing to this point. Okay, so maybe here's 0 and here's 25. This is going to end up being, well, if it decreases after this point, this is going to be a local max. And this is going to be a local min. Okay, so the only other thing that we have to do is classify these as global maxes or mins. Now our guess is that they're probably, since there are only two values, this was going to be the absolute max and this is going to be the absolute min, but let's go ahead and go through the process anyway. So I'm going to make a table. I'm going to do T and C of T, and I'm going to put my two values on there, 0 and 25. When I put in 0, I get out 6,000, and when I put in 25, I get minus 165, comma 875. Okay, so indeed, this is going to be an absolute max, and this is going to be an absolute min. Okay, but now keep in mind we have to answer the question, find the maximum and minimum oxygen content during this time. Well, we determine where the absolute max and min occur, but the absolute max, the maximum amount of oxygen is this, and the minimum amount of oxygen is this. Again, I don't know what these numbers mean in context exactly, but we can just answer it. So we can say the max is 6,000 at time 0, and the min is minus 165,875 at time 25. Okay, just to make sure that we answered the question. Okay, so optimization, the idea is go through, do the same process, classify as local max or min, absolute max or min, and go from there.